Implicit differentiation is a very easy extension of the general idea of taking derivatives, and in fact I've already mentioned this in an earlier class. And it is actually a very simple way to do it. It's a very simple technique, but it's very, very effective and very powerful, and it allows us to do all kinds of computations and allows us to achieve all kinds of goals in a relatively simple way. Now, what we're going to do in this class is just formalize what we've seen before in terms of what implicit differentiation is, and I'm going to preview a little bit the uses that we're going to make of this technique in the future. So just to formalize what we saw before, implicit differentiation is used when x and y, the two variables, are related not through an explicit function of the form of y equals f of x, but through some kind of an implicit equation where x and y are linked in the equation, but we cannot untangle them, or maybe it's difficult to untangle them. Okay? Now remember that in this situation we're thinking of y as the dependent variable as usual, which means that y is actually a shorthand for a function of x, and that's very important to consider when we implement the technique. So how is the technique implemented? What we do is we start from this equation that links x and y, and we differentiate both sides. Now, as we do that, we have to remember again that y is a function of x. So whenever we have to compute the derivative of a term or a factor that involves y, we have to remember to use the chain rule, because y is itself a function of x. So is whenever used, it's going to be sort of the inside of something else. Now, when we do that, we always end up with a linear equation in y prime. Because of the way the chain rule works, this procedure will always produce an equation in y prime. And therefore, what we are going to do is we're going to end up with an equation which is very easy to solve for y prime. Okay? And so all we'll have to do is pretty much isolate y prime, and that will give us what y prime is, even though we may not know what y is, which is kind of wonderful. Now, just as a very quick example, just to show you why, in fact, how it is done and how the chain rule is used and how easy the equation turns out to be, here is a basic example. We're going to see some more in class. So let's say that x and y are related through this equation. Now, notice that this equation actually is not even particularly complicated. If you notice, this is a quadratic equation in y, so we could, in fact, reorder this equation and solve it for y, but of course that would give us a plus or minus, and it would involve a square root and all kinds of things that make derivatives complicated in an explicit way. So instead we're going to leave the equation as is, and we're going to differentiate left and right hand side by using regular differentiation rules plus the chain rule whenever y is involved. So if we differentiate it, this is what we're going to get. Now let's notice how this works. So we have a cosine of x cubed. Well, that's easy. We're going to use the chain rule there, which gives us minus sine of x cubed times the derivative of the inside, which gives us 3x squared. For the second term, this is a product. It's a product of x and y squared. So we have to use the product rule. The derivative of x is just 1, so that we're left with just y squared. And the derivative of y squared is going to be 2y times the derivative of y, which is y prime. Remember, y is involved, we need to use the chain rule. And then times, of course, the first factor, which is x. On the right hand side we only have y, so its derivative is just going to be y prime. Now be careful not to take the derivative of y as being y times y prime, because that's not correct. Remember, we're asking for the derivative, and so the derivative of y is simply going to be y prime. Now notice that y prime only appears with power 1, only appears on the outside, and therefore we can solve this equation by simply isolating y prime. So what we do is we use the usual procedure of putting all the terms with y prime on one side and all the terms without y prime on the other side, and then we factor out the y prime on the left hand side and divide by what is left over from the factoring, thus giving us the formula for y prime. Again, notice that we now have a formula for y prime without even knowing what y is as a function. However, notice also that this formula involves both x and y, so it's still kind of an implicit formula. But again, this is not going to create a problem in most of the applications. Now, speaking of applications, what do we use implicit differentiation for? Well, of course, to find slopes of curves that are not functions. That's what happens when you have an equation linking x and y not in an explicit form. Most likely, not always, but most likely that means that we're dealing with a curve which is not a function. However, that curve still, we can talk about the slope of that curve and so on, and so we can try to find the slope of such tangent lines or of the curve by using derivatives. The other applications that we've already seen, but we're going to see again in the future, is it's used to find derivatives of inverse functions, and we've seen how that works. Then we can use implicit differentiation if you want to compute the derivative of functions which have some complicated features that can be simplified by logarithms. If you remember, this is another method called logarithmic differentiation, and which is based entirely on the idea of implicit differentiation. So this is another application. And then related rates problems. So related rates problems are something that, again, we're going to see a very simple example in class, hopefully if we have time, and otherwise we're going to spend a couple of classes on it. So we're going to see this method of implicit differentiation being used extensively, while at the same time we review how to solve word problems.